All right, this next example, they want us to approximate this infinite sum over here with this partial sum, which you can see is at 100. So they want us to know, or they're asking the error bound is positive or negative, and by knowing that, is the approximation going to be an overestimate or underestimate? And then what is the absolute value of this error bound? Well, let's find that error bound first. We know if we're going to find this error bound, it's going to be the next term. It should be less than the next term. So the next term here would be 1 up from 100, which would be the 101st term. So we're going to want to plug in 101 in for n to find that next term. So for both n's here, let's plug in 101. So if we simplify that, that's going to end up being the -1 to the 102nd over 101. A negative number to an even power is going to make that equal +1. And so this should be whatever 1 over 101 is, which is going to come out to be a positive number. And so we know if this error comes out to be positive, the approximation must be less than the actual value. So hence this is going to be a underestimate of the actual number. Okay, so let's find out what that estimate actually is. So if we want the absolute value of this, it's not going to really change much. Absolute value is still going to be just 1 over 101 here. And so we know if we go to our calculator here and do 1 divided by 101, that this partial sum should be within, or the error bound should be within 0.0099. So our error bound on this one, our error bound is approximately 0.0099. So we know the sum of 100 should be within 0.0099 of this infinite actual sum over here. All right, let's have you guys try this one out. So they wanted you to approximate that infinite sum with this partial sum from 0 to 3. And then also see if you can answer if the error bound is either positive or negative. So is it an overestimate or underestimate? And then what is that actual error bound? All right, hopefully you've had a chance to try this. You can see here that this is the sum to 3, so we want to use that next one. So we want to use a n of 4 here in order to do that. So place 4 in for the n, which means we're going to have -1 to the 5th power over 9 factorial, which is going to end up being a negative value here. So our error bound is going to be negative. And so that means our approximation here should be a overestimate of the actual value. If we go through though and do the absolute value like we should when we're doing an error bound problem, that means it's going to be the absolute value of this, which is just going to be 1 over 9 factorial. And if you put that in the calculator, which I already have here, it looks like you get 2.755 e to the -6, capital E to the -6. When your calculator gives it to you like that, what that means is you got 2.75 times 10 to the -6 power. So what we'd want to do here to find the actual value of this is move that decimal place over 1, 2, 3, 4, 5, 6 times. So all these spots should get replaced with zeros here. So there should be, or that error bound should end up being approximately 0.000. There'd be 5 missing zeros there, and I'm going to round that to 3. So our error bound should be within that much of the actual value. So ours is actually fairly close to the infinite sum there, out to that many decimal places.